Hi, AP Calculus and also Calculus class. So today is November 17th, 2022. You're probably still gone from Ho Chi Minh City on your Week Without Walls trip or on the way back to Ho Chi Minh. But nevertheless, this is going to be like the makeup video for this week of the November 14th to November 18th week that you're gone for this field trip, all right? So please, as you watch this video, take good notes. We will be talking about implicit differentiation. And this is very, very important because we have to get really good at this before we can get into the more difficult real-world applied problems, like optimization and maximum and minimum problem-solving problems that will require implicit derivatives, all right? So let's get started. So a lot of my students have asked me, okay, when it comes to taking a derivative, a lot of you have been asking me that, okay, teacher, what happens if I'm using the chain rule and I have a function and I don't even know where to stop? And that's a very good point to make because, for example, if you have something like f of x is equal to, okay, let's say sine of x to the power of 3. And you also have another one, g of x, okay, is equal to sine of x. So obviously, these are two different, functions, and they're looking similar, but one has something inside this parentheses, and the other one is just your normal sine of x function. Now, obviously, if I'm doing this one, the derivative of g of x, then I know that based on the property I gave you, the trigonometric derivatives, that this would simply just be then cosine of x, right? So I know where to stop on that because I'm just following the equation that we've been given before. But then what about this one? Okay, I mean, obviously we can have a lot more complicated functions in this, where there's a lot more stuff in there. But how do I know what form I should leave it in? Because some of you had done the previous homework assignments and you weren't quite sure, oh, should I stop here or should I make the fraction look a little prettier or should I get rid of the exponent? Should I, how can I finalize my, final answer, right? After you'd use the chain rule. So for example, if I'm looking at f of x, and I see, okay, this situation here, and I don't know where to stop. So let's do the derivative of that first. Okay, so what I'm going to do is I'm going to try to use the chain rule this way. So I'm going to do, of course, we know that this is going to be a cosine when I do the derivative. So it has to be cosine of something, as we already know. And that one would be then whatever is still inside the parentheses, right? And then I would need to then do the derivative of what's inside here. That would be then d of x to the power of 3. There we go. And that's all over. Not all over, but let's make that over. D over dx, okay? Because I'm just doing the derivative of whatever the heck was inside the parentheses with respect to x. Okay, when we do that, we say with regards to the x variable. Okay, so then that will become then, just to remind yourself what we're doing here, that would simply be then, again, okay, that would be cosine of x cubed. Okay, and then that would be then times the derivative of what is this thing here. So that would be then a 3x to the power of 2. I still have then this is with respect to x, so I would have this left over like this. This is to imply that I had already taken the derivative of whatever that was, okay? So this is kind of a more formal, lengthier way to really show people what we're meaning when we're doing a derivative, okay? I mean, really what it comes down to is when we are doing like this, this is telling you that when we get to this part, because this f prime of x is really the same thing as dy over dx, right? So this is trying to let you really know what dy over dx or f prime of x really stands for. It's not just saying that, oh, I took the derivative and I'm done. It's more like that what I was really doing was I had some kind of original equation. And what I was really doing was I took the derivative of both sides of an equation, okay? So that's really what we were doing. We were doing the derivative of f of x. But anyhow, let's finish this one up and clean it up a little bit. But then f prime of x is equal to then just this then, if I can say that d of this, okay, so let's not make it go that far. I want to just say that this is still d over dx of just x itself. So basically, for this part here, this is just, it seems redundant, but it's just telling you that you did do the derivative of that with respect to x, okay, of whatever was the content, you know, that was inside the parentheses that had the x variable. Okay, so anyhow, f prime of x then will be simplified if this part here, I'm going to write this in another color. If we make sure that we remember that d of dx over x is simply equal to 1, okay, then this part here would just be 1, correct? So then this will clean up to become cosine x to the power of 3 wow, okay. And then that would be times 3x squared. They don't like the 3s, do they? All right, that's times 3x squared. Got it? And then this is all 1. So then this is where we know that I've done everything I possibly could, and I can stop here. Hopefully that gives you some little bit of more insight as to like where is a good place to stop when you're using the chain rule, okay? Anyhow, that's not really the new topic yet. Now we get into the new topic of implicit differentiation. So what that means is when you have an equation, okay, for this example, let's do one more function that's not something that you can't do. Okay, so I'm going to move on to, let's say, the second function. I'll have an e to the x here. Brown color. Okay, so let's say I would do this equation. 4x to the 5th plus e to the x. Okay? So this one, if I'm doing derivative, this isn't going to be too hard, but I'm going to show you how I'm going to do it in a more formal way, you know, using what we learned already from all the techniques that you learned up to this point, okay, in this chapter. So when I'm doing the left side, I will rewrite this as d over dx of just the y, because that's all I see on the left side of the equation. Then on this right side, I will then just do the derivative with respect to x of the entire 2 terms. So I will write it like this, of 4x to the 5th plus e to the x. Okay, so I just put all that 2 terms in this parentheses, and then d over dx is just outside of that. This is a formal way to take the derivative of both sides of this equation. So after this, I'm going to now remember that this part here, or this part here, d of dx of just y is simply the same thing as just dy over dx. So always remember that much, okay? So this side can now be written dy over dx. And then now I can do the derivative of my content or the terms inside my parentheses. So then that would be then power rule, 5 times 4, which is going to be 20. And then x to the 1 power less, that would be to the power of 4. Okay? And then I will still multiply that I did the derivative already. And that would be d over dx of my x variable. Then this next part would be plus this derivative here, which we know from our exponential function derivative, that would simply just be e to the x. And then we need to times d over dx again to imply that we already did the derivative of the x variable. Okay? Yeah, so there we have it. d dx plus e to x. And then simplify. Okay, dy over dx is equal to, then this would be, now remember we saw this before, this is the same thing as dx over dx, so that just becomes 1. That would just be 20x to the power of 4. That's times 1. And then plus, right? This one also becomes just 1. Right? So that would just be e to the x times 1. And then final answer is 20x4 plus e to the x. And there you go. Okay. Now, this is still something that you didn't have to do it this way. I could have simply have done that in a shorter way by doing just normal differentiation of these two terms, because why? This was expressed as a function where y is set equal to x explicitly. Okay. This is an explicit relationship between x and y. So what we mean is that we know exactly what y is in terms of x. Okay. But let's say though, we get equations where it's not this nice, where I could have y and x mixed up on both sides of the equation. And then so we would have something a lot messier, because really we need to have the y's and the x's separated in an equation in order for us to do the derivative more easily. But in case they are not, and they're all mixed and jumbled together, then we need to treat that equation as an implicit equation. So it would be an implicit differentiation that we must solve. Let's say we have this situation, class. X squared plus y squared is equal to 1. So clearly the x and y are jumbled together. Now, if you want to make your life easier, if you want to make it explicit, so this is implicit, right? Because the x and y are jumbled. But if I want to make it explicit, then I would move the x to the other side. So that would be y squared equals 1 minus x squared, right? Then I know that y would be simply plus and minus the square root of 1 minus x squared. And this would be the explicit version, okay, of the function of the equation. But actually it isn't a function though, because you know, if you remember from pre-calculus, x squared plus y squared equal 1 is really the equation for a circle. And a circle, as you should know, in the xy plane looks like this, but it fails the vertical line test, so it's not a function. Okay, but anyhow, if I'm going to do the derivative of this, I can, okay, especially when it looks like this. But then we're going to learn here how we can do the derivative of this equation, okay, by using implicit differentiation. So instead of having to look at the original equation and then moving the x to the other side and then isolating y from x and then having it look like this, what if I just left it as x squared plus y squared equal 1? So I would take the derivative just the way the equation looks. Then that would be called implicit differentiation. And so when we do that, I'm doing the derivative of both sides of the equation without having to move anything around, okay? But we're still going to have to be able to use our chain rule wherever we need to use it, as we are doing the derivative of both the left side and the right side of the equation. So let's try another problem with this same equation again. All right, so I've got x squared plus y squared is equal to 1. This time I ask you to find the slope of the tangent line to this equation, okay? So That's all you need to do is find the slope. So it's really all you're doing is taking the derivative. I want to find dy over dx, just like you've done before in the previous several lessons. So I will not move things around to the other side. I would just leave it as it is, but I would do the derivative of it. You understand? Okay. So I would do the derivative of this equation without moving the x or y on other side. So let's do the derivative of the left side. D over dx. So annoying. That would be then of all this stuff on the left side. And then that's all equal to derivative of that constant 1. Okay, and then that's how I start off the implicit differentiation. Now I'm going to use a chain rule wherever I need to. So here, okay, I will do the derivative of this one here. That would be 2x, right? And then that's times d over dx of x to show that I did the derivative of that already with respect to x of the x variable. Then I do plus, we'll do this guy next, 2y, because that's a derivative of y squared. And then I need to do this as well. That means I was taking the derivative of the y variable with respect to x. And then on this side here, it's a derivative of just a constant, so that would just simply be 0. Okay, that gets rid of faster. Now, with that said, I know that this here is going to be equal to 1. And then over here, this d over dx over y is the same thing as dy over dx. So I can rewrite this again. This will just go away. That would just be 2x. And then plus over here, that would just be 2y dy over dx all equals 0. Now, if I'm going to solve for dy over dx, just do them algebra. So here, I'm just going to isolate this by itself. This would be negative 2x if I move it to the other side. That means dy over dx will simply be negative 2x divided by 2y, which is going to be just negative x over y. So this is my slope. Okay? That is it. That's the slope of the tangent line that would hit the circle, okay, at some point. Now, this is the slope of this. Now, let's visualize what this will look like. Here is a picture of that equation, x squared plus y squared equal 1. Now, as you can tell, and let me make this a little smaller. As you can tell in this circle, because the equation that we got here is in a derivative that has both x and y in it. And if I ask you in this question, find the slope of the tangent line to this equation, okay? Then you're probably wondering, like, let's say if I ask you then to find the derivative of this when x is equal to, let's say, 1/2, okay? So if I need to do the derivative of this equation at x equal 1/2, you might have more than one point, because as you can see in this graph here, if I'm doing that and sticking this thing here, x equal 1/2, I know that there's two values of x equal 1/2 on the circle, because the circle does not pass the vertical line test. So you would have two y values for the same x point, making this circle not really a function, right? Because, you know, for every one x, you should have one y value. But this is one x value of 1/2 that gives you two y values, right? Somewhere at the top of the circle, and then another one would be at the bottom of the circle, okay? So that is where I have two tangent points, okay? Because this is not really a function and it doesn't pass a vertical line test. So that is where x equal 1/2. Okay, and then how did I get the square root of 3 over 2? Well, all I did was I put that x equal 1/2 into my original equation. So my original equation was this one. We put it back in there, okay? Now, we already did this a little bit. I was able to explicitly rewrite the equation as y equals all of this. So you can go ahead and put the value of x equal 1/2 into this equation, and you will get the plus and minus. You get two values, right? I get one up here and one down here. So that's why in this graph, you would see those two y values. And then, so if I'm doing the tangent line at those 2 points on the circle, I would need to also get two different slopes. I get a slope of this one, which would be a negative slope, and I would get a slope of this one, which would be a positive slope. So let's go ahead and actually do that, okay? But when I'm sticking in this into my derivative, I need to use two different dots, this dot here and this dot here as well, okay? So let's do that on the next page. All right, so what I'm going to do is I will take then dy over dx, okay? This is at one point, so we know it's this, right? If I do the first point, let's say I do the top one with the positive y value, then this would be negative, and then that'll be 1/2 divided by my y value, which is the square root of 3 over 2. Okay, if you don't know where I got that number from, you need to go back and put x equal 1/2 back into the original equation. This would be one of the y values that you get. Okay, so yeah, anyway, so it's the square root of 3, okay, over 2. And then that's the same thing as then what? That would be the same thing as negative 1/2, right? Times 2 over the square root of 3, correct? That will cancel. That will give me negative 1 over square root of 3. That will give me the negative square root of 3 over 3, okay? And then that would be the slope, okay? One of the slopes. That would be the slope then at the top of the circle, okay? So the slope over here would be then, this slope here, I'm going to write it in, would then be m is equal to negative square root of 3 over 3, okay? With this tangent line. All right, the other one over here, so over here, let's do then the other point. We have another y value that's negative. So I'm going to do that now. This is my second slope. That'd be negative or 1/2, right? Divided by negative square root of 3 over 2. That's the same thing as then negative 1/2 times 2 over the square root of 3. That's a negative 2 here. That will cancel out, and then the negatives will cancel. So you just get a positive 1 over square root of 3, which is equal to the square root of 3 over 3, right? So going back to that picture, my slope over here, okay, this would be then m is equal to the square root of 3 divided by 3, right? That is going to be the slope, positive slope there. So here we have it. That's how we will use implicit differentiation to get then the derivative or the slope of the tangent lines at these 2 points on the circle. All right, let's continue on to the next thing. Now, for these 2 problems we just did, and going forward, I know it seems redundant when we were doing d over dx of whatever, We obviously had so much stuff to write, but let's not have to do that anymore. I only did that for the first two examples so that you could see that we are doing literally, term by term differentiation on both sides of the equation when I'm doing implicit differentiation. But let's do those two problems again. But this time the shortcut version of that without having to write so much. And this is the shortcut method of implicit differentiation I want you to use going forward. And so it'll make your life a lot easier and not have to, do so much redundant writing, okay? You see in a minute what I'm talking about. Okay, so let's go back to this equation here. Let's do it let's just do the derivative now on both sides of this equation. If I do the derivative of y here, it just simply just be then derivative of that is 1 times dy with dx. Then this here, I would then do 5 times 4, x to the power of 4, plus e to the x. That's just the derivative right there already, yes, okay? And so then this means that dy with dx is equal then to, this would be 20 x4 plus e to the x, and when we're done. Now, this is the normal way that we did it without having to be redundant, right? This is the way that you guys are used to, we learned the last several weeks. Now, let's try to do that same thing with the circle equation that we had earlier without having to write so much, okay? All right, so let's try that with the circle equation again. X squared plus y squared equal to 1. So doing the shortcut implicit differentiation, just do the derivative of that, 2x to the power of 1. And I'm not even going to bother to write d over d. I was going to do this before, but I will ignore this now and no longer do that anymore because I want to find a way to do a more straight to the point shortcut way of doing implicit differentiation. So that would just simply just be 2x. Then, however, whenever I have a y though, I will not just only take the derivative of that, which is just 2y, I will still need to multiply that times dy over dx, okay? And that then would be equal to 0. I'll just do derivative of 1 directly and it'll just be 0. It's a constant. Okay, so now that leaves me with just this. So I'm going to move the 2x to the other side. That would be then a negative 2x. Then if I isolate dy with dx, the derivative, then I will have then negative 2x divided by 2y, which is simply equal negative x divided by y. And we have the same thing that we did before when we did the longer version of the implicit differentiation. Now, another way you could do this, and I'll write this in orange, the shortcut way, is not even use the dy with dx. I might just go like this, 2x plus 2y times y prime equals 0. Then I would be left with 2y times y prime equals then negative 2x, then y prime is equal to negative 2x over 2y, and that would just simply be negative x over y. So I could just leave it like this. Y prime, which is derivative, it's another way to write dy with dx, which is simply equal negative x over y. Either way, it's still the same, and that is an example of how you do a shortcut to implicit differentiation. All right, now going forward, let's do some more. And then the next step we're going to do it without using the long way, but the short way of implicit differentiation, okay? So the next problem we're going to do is going to be then this equation. Let's say we have natural log of y plus cosine of y equals 3e to the x minus x to the power of 3. I want you to find, right, dy over dx, okay? So this is an equation where you definitely don't want to try to isolate y by itself, right? It's kind of hard to yank y out of both of these. I can't factor a y out of something that's stuck inside the natural log and the cosine. So I have to take implicit differentiation of this, okay? The way the equation looks without moving things around. So let's start with this equation. If I'm doing the derivative of this, okay? So let's start with this side here. Over here, this derivative would just be using your derivative rule for natural logarithms. That was simply 1 over y. And then, because I'm doing this with respect to y, I still need to write dy over dx, okay? Now let's do the second term. That's a cosine function, and you know that from your trigonometric derivatives, that the derivative of a cosine function is a negative sign, okay? So this would simply just become then plus negative sine of y, okay? And then that would be still, because it's a y variable, it would have to be times dy over dx, okay? Now on the right side, this part here, this is a constant, so that just stays there. But e to the x derivative is just e to the x. We had proved that already before, right? A few lessons ago. So then that would just simply be just e to the x still. And then that 3, this actually would be treated like the product rule, but you would still have a 3 stuck onto whatever in front of e to the x, okay? So you could do this separately as a product rule, multiplication rule of derivatives, but you still end up with this final answer, 3e to the x. So that would just be 3e to the x. This part here is a power rule, so bring the 3 down, and then that would be to the power of 1 less, which is 2. So that would be simply minus 3x to the power of 2, okay? So far, so good. This equation is looking not so bad. I need to isolate dy over dx by itself, so I'm going to factor dy over dx out. That would be then like this, and then I will have this left over, 1 over y minus sine of y, okay? And that's still all equal to this stuff on the right side, right? Okay, so I have one last step. I want to isolate dy over dx completely by itself. So I have one more step to do. That would be then dy over dx is equal to then all this divided by this, right? All that divided by all this stuff here. Okay, so now this looks kind of ugly with that in the denominator. So I could multiply everything in the numerator and denominator by y over y, which is y divided by y is simply equal to 1. But I can make it and look a little bit cleaner and not so ugly. So that would be changed then to 3y e to the x minus 3x squared times y. Everything is times y in the numerator. And then do the same thing at the denominator. So if I took y times this, it would just be y divided by y. That would simply just be 1. And then this y would just be multiplied in front of that. That would be y sine of y. And that is your final derivative of this after we finish our implicit differentiation, okay? All right, let's do another problem. So let's say I have this equation. And I want you to find the slope of the tangent line, okay? Find the slope of the tangent line to this equation, right? At the point 1, -5. That's a very specific Okay, I mean, look, did a better 5 earlier and it didn't look so good. Okay, so that's at 1, comma, -5. That's your xy point where you want to have your tangent line drawn to this equation. So again, start with exactly what you see here, right? And then go ahead and do the shortcut version of the implicit differentiation. So I'm going to write that now in green. Now, derivative of this part here, I would need to use the product rule because it's y squared multiplied natural log of x. So do the derivative of the y squared first. That would just simply be 2y. And then this carries over. I don't do anything with that. Then according to the product rule, I have to do, before you do that, since I do the derivative of a y somewhere, don't forget that I need to include dy over dx because I did have a derivative of the y. Whenever I took the derivative of the y, then I need to do that times dy over dx to let people know that I already took the derivative of the y with respect to x. Okay, so that just takes care of the first part of the product rule. Then I will then add, okay, to this part again, times the derivative of this thing, okay? That would be 1 over x. I don't need to write d over dx here because I'm doing the shortcut version. And then you know the derivative of that is just simply going to be then 1. So that's just 1 times dy over dx. This 5 would just be a 0 because it's a constant. So that is the second step so far. And then now I need to isolate the dy over dx. So I need to move the dy over dx together on the same side. So I will have this next. Then minus, okay, this dy over dx. Okay, and then I'm going to move this guy to the other side. That would make it a negative y squared, okay, and 1 over x. Okay, so I don't need to keep going from here, if you can tell, because y, I already have a point that I could just stick into my equation. You understand? So let's do that right now. Let's just use this form here, okay, and start putting in the x equal 1 and y equal -5 over there. So I would do 2, okay, times -5, right? And then that would be times this stuff here. So that would be then the natural log of x. X is 1. So 1 will go in here, right? And then times dy over dx. Okay. Then we will add, no, we still do the add part. So the y squared now, the -5 will go in for the y, correct? So that would be then -5 to the power of 2, and then times 1 divided by x, which is 1. That's all equal then to this thing still, dy over dx, right? So we can clean this up a little bit more. So with this, we're going to now make that become then, okay, now keep in mind here, what is this, guys? Natural log of 1 is just 0. So 0 times all this will go away. That will cancel out and we'll leave with this part. -5 to the power of 2 would just simply be 25 times 1, right? That's 1 over 1, that's still 1. That's all equal to dy over dx. And then this is done. This is going to be the slope of the tangent line at the point 1, -5. So this 25 is the slope of the tangent line at the point 1, comma, -5. And that example is now finished, right? Okay, the next example we're going to do is a more difficult trigonometric, I guess, function, okay? And I kind of worked this out already so that it will go a little bit faster. This is the original equation here. Tan of y is equal to cosine of all this stuff here. Okay? So with this part here, what I'm going to do is implicit differentiation of both sides of the equation. So my next step would then just be, this would be, if you use your handout I gave you, right, the derivative of the tangent function is just secant squared, okay? So this would become a secant squared of y. And then because I'm doing the derivative of y here with respect to x, that becomes dy with dx, right? Don't forget to put that always there. Whenever you're doing implicit differentiation and you're doing derivative of a y, make sure you add that dy with dx. On the right side, let's treat this cosine function as just a cosine function first. So don't worry about the content inside there at the beginning. So from your trigonometric derivative rules, you know that the derivative of the cosine here will just be the negative sign of whatever is inside. So rewrite all that here again, okay? And then we need to then times, using the chain rule, the derivative of what's inside this parentheses, which is all this. This is an x multiplied sine of y. That's the product. So we have to use the product rule. So I would do this product rule inside these big brackets. So this would be the derivative of x, which is just 1. And then this carries over times sine of y. Then I do the plus sign. And then I'll carry over the x here unchanged. And then this will be now done the derivative of sine of y. It's just cosine of y. But because I took the derivative of this thing with a y, don't forget your dy with dx over here. Okay? Then, going to the next step, this will stay the same on the left side. Now, I can use my distributive property from algebra to multiply this thing on the outside of the brackets times everything inside the brackets, this term and this term. They're separated by addition. So take this, multiply that, and then add it to this times that, okay? Distributive property. So if I take this times this, it becomes all this again. And then this 1 will just be 1, but whatever, we don't have to write 1 again. That would just be times sine of y. Now you have this plus sign here, but because this is a negative number and a positive, then that would still be a negative number. So it'd be all this stuff here, multiply this stuff here. So I just lump them together like that, okay? Okay, then again, next step, this side on the left has a dy over dx, but on the right side, this term has a dy over dx. So I should put everything that has a dy over dx together. So this is me putting them together. That left side will stay the same here, but I'm gonna move this part here over here. So I just moved it and now it's all positive. And then we still have this part over here on the right side of the equation. That I copied it down unchanged, right? Does not change at all right there. All right, now I got the dy with dx terms together on the same side. So now if I want to isolate dy with dx, it will equal this stuff on the right side, that's here, the numerator, all divided by the secant squared y plus all this stuff here, which is the sine of all that. Okay, and yep, it doesn't look nice, but this is now dy with dx separated out, and I'm done with the derivative of this. So this is your final answer for this complex sort of trigonometric derivative problem. So remember, it started like this at the very beginning. And then I was doing implicit differentiation on both sides of the equation, being very mindful of the product rule and the chain rule, okay? And then I isolate dy with the x by itself once I have everything kind of multiplied out, and I'm left with this. So that problem is now done for this complex trigonometric method. That leaves one last problem then. This is now to deal with the derivative of the natural log of x. Now, if you remember, a long time ago, not a long time ago, when we did e to the x function, and we once proved that the derivative of e to the x is just e to the x. Remember? Because you guys did that for my assignment the week before, where you need to do different points along that exponential function. And then you were able to get like tangent, right? Of these points along that curve, and then show that when I take the derivative of this and doing the slope of the tangents of these tangent lines, you still get the original e to the x function. Right? Now, we're going to prove, using this proof, that the derivative of the natural log of x is equal to 1 over x. Okay, let's start with the equation first. Y equals natural log of x. Then what I'm going to do is I'm going to take e to the power of both sides. I'm going to take e to the power of y and then e to the power of the natural log of x. Now, this part here is a trick here because I know when you look back at the curves of e to the x and then down here, this is the natural log of x graph. Remember, these two are similar curves. They're like mirror images of each other. Their line of reflection is the y equal x line, right? But they are inverses of each other because they're mirror images of each other here over the line y equal x. So we know then that if I'm doing e to the power of natural log of x, because they're inverses, then the answer would just be whatever content is inside a natural log, that's simply just going to be x. So this part over here can just be now changed to x. The left side is still e to the y. And then I will now do the implicit differentiation over here. Okay, so we start to do implicit differentiation over here. Okay. So then this part will be e to the y. Okay. Because that derivative of e to the y is still e to the y. But then because I took the derivative of this y term, I need to still write down dy over dx, okay? You still don't forget dy over dx. And then this side here, derivative of x is just 1. So that'll just be 1. And then I can isolate dy over dx by itself. So then this would be on the left, but 1 divided by that is equal to this. But because I already defined that e to the y is equal to x, that means that then I can rewrite this part as also 1 divided by x. And now I prove that the derivative is equal to 1 over x, which means that my proof is done because I proved that the derivative of natural log of x with respect to x is simply equal to 1 over x. Okay, and so we finished that proof already for this so-called, original derivative equation that we were given on the handout. Okay, so we didn't use the graphical method like this, like we did e to the x. We use instead implicit differentiation to prove this. All right, so hopefully that makes sense now for like the start of what is the chain rule and implicit differentiation. Okay, used to help take derivatives of jumbled equations of x and y. Okay, so we will do more problems for sure, right? In class time, when I see you again, this is enough now. This is like, I don't want this to be longer than 1 hour. Consider this to be part 1 of your first introduction to implicit differentiation. And we'll do more examples either in class or in the next video. But this is all for now. You got a good taste of what implicit differentiation is. Please, I hope that you took good notes on this video. And then once you've done that, we can give you some homework assignment to do more practice problems. But I will probably cover a little bit more examples for you before I give you that assignment or a pop quiz. But anyhow, we're done with this first part of implicit differentiation. Thank you for watching, and I will see you guys soon.